For this question, it says, a skull cleaning factory cleans animal skulls of deer, buffalo, and other types of animals using flesh-eating beetles. A factory owner started with only 6 adult beetles. After 50 days, the beetle population grew to 18 adult beetles. How long did it take before the beetle population was 6,000 beetles? So we're going to assume that this model is an exponential model. And using this information right here, that we started with 6 beetles, and after 50 days, that beetle population grew to 18 beetles, we're going to be able to find the growth rate. Okay, so what I'm talking about with an exponential model is that it will follow A equals A naught e to the kt. Let's start with A naught. A naught is the initial population. T is time. And K is either the growth or decay rate. In this example, we're starting with 6 beetles and it grows to 18 beetles, so this is a growth rate. And when we do our calculation, when we have growth, K will come out to be positive. If you ever have your population getting smaller, it will be called a decay rate, and K will be calculated to be negative. So with this information from the beginning about starting with 6 adult beetles and after 50 days the population grows to 18, we're going to be able to figure out what the growth rate is. And then once we know the growth rate, then we're going to be able to answer the question that's posed on the second part, which is how long did it take before the beetle population was 6,000 beetles? So let's start with finding the growth rate. So we start with our formula, A equals A naught e to the kt, and we know A naught is the initial or beginning population of 6. A is the ending population or the accrued amount, and that is going to be 18. And we also have a time of 50 days. So we substitute that time in. We have an exponential equation because our variable is in the exponent, and we're going to solve this equation using the methods of exponential equations. So we start by isolating the exponential part. So this part is the exponential part that has our variable, and we want to isolate it. So we're going to divide by 6 to get 3 equals e to the 50k. Then we'll continue to solve. We have different methods that we could use for solving exponentials. The basics are trying to make the bases the same, which we can't do in this example. We can convert it to a log or take the log of both sides. Either one of those methods you could use. I'm going to take the log of both sides. So I'm going to do natural log on the left and natural log on the right. On the right-hand side, I can use the power rule and move that exponent to become the coefficient. That becomes 50k, natural log of e. I can simplify this further because natural log of e is 1. So that becomes 50k times 1, which is just 50k. And then I can divide both sides by 50. So now I've found the growth rate to be natural log of 3 over 50. Now I don't want to use the approximated value, but I want to show you that when we type this in your calculator, natural log of 3 divided by 50, we get that positive value for the growth rate. I'll go ahead and I'll round it to 0.022. That's approximately 0.022, but you never want to round until the very end. And so I'm going to use this in my calculation rather than this value. All right, once I have the growth rate, then I'm going to be able to answer the second part of this question. How long did it take before the beetle population was 6,000 beetles? So we can take our formula again. A equals A naught e to the kt. Remember, we now know the growth rate to be natural log of 3 over 50. The question says how long, so that means that the thing that we're looking for in this problem is time. And so then we've got how long does it take for the beetle population to reach 6,000? So that is our value of A. That's going to be the 6,000. Our initial population, remember, is 6. 6 beetles to start with. So we have everything except for the variable we're trying to solve for. So I'm going to substitute 6,000 equals 6 e to the natural log of 3 over 50 t. This is once again an exponential equation. We're trying to solve for a variable that's in the exponent. We're going to solve by isolating the exponential. We're going to divide both sides by 6. That's 1,000 equals e to the natural log of 3 over 50 t. Once again, I'm going to take the natural log of both sides to solve the equation. Once again, I can use the power rule to bring that to the front. Natural log of 1,000 equals natural log of 3 over 50 t. Natural log of e. Natural log of e is 1. We have natural log of 1,000 equals natural log of 3 over 50 t. Natural log is 1, so that's why that went away. 1 times anything is itself. And then I'm going to divide both sides by 50. I'm sorry, not just 50, that whole coefficient. I'm dividing by natural log of 3 over 50. That cancels this coefficient out, leaving me with t. And here I'm dividing by a fraction. When we divide by fractions, we can multiply by the reciprocal. So that's 50 over natural log 3 times natural log of 1,000. And I'm going to type in my calculator 50 natural log of 1,000 over 3 to see what that time is. Yeah, 50 natural log of 1,000 divided by natural log of 3. We have 314 days It will take 314 days for our beetle population to grow to 6,000 beetles. For this question, we want to use the properties of logarithms to expand the logarithmic expression whenever possible and evaluate the logarithmic expressions. The expression we have is log of square root x over 100,000 y to the fourth. So the properties that are being described here are properties of logarithms called the product rule, the quotient rule, and the power rule. And these properties are explaining how you might deal with simplifying or rewriting multiplication, hence the name product, division, or a quotient, which is why it's got the name quotient rule, and also a power inside the log. So you need to know these three properties. And when you have a product inside of the log like you have here, what you can do is you can expand it into multiple logarithms that you then add together. Now what goes in each one of those logarithms are the factors. So you can see this is a factor of m, and m is inside of this log. We have a factor of n, and n is inside the second log here. So we can expand this logarithm using this product rule for logarithms. Then we have the quotient rule. So if we have division, we're going to take the factor that we have in the numerator into one log and the factor that we have in the denominator to the other log. But I want you to notice, very importantly, that there is a minus here instead of a plus. So that minus is on the factor from the denominator only. So anytime we have a factor from the denominator, you're going to have a minus in front of that log. And then the power rule allows you to take this power and make it the coefficient on the log. So it's almost like plucking it. You can imagine grabbing that symbol from the exponent and moving it to become the coefficient. And so that's what we're going to use to simplify this expression or expand this expression. So the first thing I want to take note of on our example is we have a square root. Square rooting is the same thing as raising something to the 1/2 power. So this is the same thing as log of x to the 1/2 over 100,000 y to the fourth. Okay, so we're going to need that later when we use our product rule. The power rule. So then what I want to notice is I'm going to start by using the product and the quotient rule first. And so because I'm going to use that product and quotient rule first, I want to look inside for anywhere there's multiplication or division. So I notice that I have a factor here with division, another factor here, and another factor here. So those are all my places that I have multiplication and division. And because I have 3 different factors here, I'm going to expand to 3 different logarithms. Each one will have a different one of these factors. So we're going to have log of x to the 1/2 excuse me, my pen's acting up. Log of x to the 1/2, we're going to have log of 100,000. And we're going to have log of y to the fourth. And we're going to put pluses and minus signs between these depending on whether the factors came from the numerator or denominator. So remember down here with the quotient rule, let me erase this so it's not quite so messy, that the factors that come from the numerator are going to have a positive log. However, the factors that come from the denominator will have a negative log. So these two factors that came from the denominator, these two have negatives, and the first one came from the numerator, so it's positive. So now we've used both the product rule and the quotient rule at the same time. Then we're going to move on to the power rule. So with the power rule, these two have powers, and I'm going to be able to move those powers to become the coefficients. So each of those will become 1/2 log of x and minus 4 log of y. That brings us to this last one here, and this last one is log of a number. And when you have log of a number, you want to try to simplify that log. In this example, we have log, and there is no subscript written here, and that means that we assume that the base of this log is base 10. So this is the same thing as log base 10 of 100,000. And we'll do this work on the side over here. I want to figure out what log base 10 of 100,000 is. So we have a strategy where we say, I'm not sure what this equals. Let me rewrite it as an exponential. As an exponential, we would say the base of 10 to what power is equal to 100,000. And I know by counting these zeros that 10 to the 5th power is 100,000. And so that must mean that our power is 5 and that log is 5. So this is going to equal 1/2 log of x minus 5 minus 4 log of y. Thank you for checking out my videos. Have a great day.